Hello and welcome to another Electricity and Magnetism Extra Practice video. We will be discussing electrostatic equilibrium. As always, all information and questions that are used are from the Essential Calculus-Based Physics Study Guide Workbook, Volume 2 by Chris McMullen. Electrostatic equilibrium is when a system of charged objects is in static equilibrium, or all of the objects are motionless. In order to find equilibrium, we will need to account for all of the forces present, including the weight of an object as described by the mass times the acceleration of gravity, any normal forces or frictional forces that might be present, and any other forces that might be present. In order to find equilibrium, you need to consider all of the forces acting on an object. A free body diagram can help to visualize the direction of each force. Labeling the axes so you know the direction of the vectors and which components would be positive or negative. To get the x and y components of each force and to set the sum of each component equal to 0. To check for the signs of each component, this can be found through labeling the axes and determining which quadrant the vector is in, and applying algebra to get the desired unknown. For one example, a poor monkey spends his last nickel on 2 equally charged metal bananas. When he dangles the 9 times the square root of 3 kilogram bananas from cords, they are separated as shown below. Draw a free body diagram for each object, label each force and coordinates. Alright, to start, we will be examining the left banana first. We see that it is being suspended by a cord, so we know that there is a tension force from this rope. We also know that it will always be affected by the force of gravity. And we know that it is being repulsed by its equally charged counterpart over here. So therefore, it'll also have an electric force this way. I'll note that this will be positive axis, this will be negative y, over here will be negative x, and up this way will be positive y. Now, if we look at the right banana, we know that it has a tension force going this way. We know that it was also affected by the force of gravity, and it is being repulsed by its equally charged counterpart over here, so its electric force is going this way. This way is our negative x, this way is our positive x, up here is our positive y, down here is our negative y. Write the x and y sums for each of the forces acting on each object. Below each sum, write the terms of the forces. We know that if we were to cut the 60 in half, we would end up with 30 degrees on this side and 30 degrees on this side. So we know that for our left one, we have the tension from here being at 30 degrees. We have our force of gravity, and we have our electric force. So we know that the sum of the horizontal forces for the left one would be equal to the mass times the acceleration of the horizontal forces, which is going to be the force of tension times the sine of 30 degrees minus the electric force, while the vertical forces is going to be equal to the mass of the acceleration times the vertical acceleration, which would be tension times cosine of 30 degrees minus the force of gravity. Then for the other banana, we have our force of tension going here. We have our force of our electric force going over here, and our force of gravity down here. For that, we have our horizontal forces, like mass times the horizontal acceleration, which would be the electric force minus the product of the tension and the sine of 30 degrees. We also have our vertical acceleration being the mass times the vertical acceleration, which is our tension times cosine of 30 degrees minus the force of gravity. What is the tension of each chord? For example, if we were to look at our left vertical sums, we have the sum of the forces is equal to the mass times acceleration, or the vertical acceleration, which is equal to tension times the cosine of 30 minus force of gravity. Well, because this is in equilibrium, we know that the acceleration is going to be equal to 0. So 0 is going to be equal to the tension times cosine of 30 degrees minus force of gravity, which just means that the force of gravity is going to be equal to tension times the cosine of 30, meaning that they balance each other out. Now, in order to find tension, we're going to have to take this force of gravity, turn gravity into its factors, which is mass and the acceleration of gravity. And we're also going to have to divide both sides by cosine of 30 degrees. So that results in us getting tension equaling mg divided by cosine of 30 degrees. Now, we know that our mass times gravity, our gravity in this case will be 10 meters times second to the -2. And when we multiply our mass of 9 square root of 3 kilograms, we get 90 square root of 3 divided by a cosine of 30 degrees, which when you plug into a calculator gets you an answer about 180 newtons. This is going to be done with the right one as well as the vertical force, or the sum of the vertical forces will also have a 0 acceleration, which is equal to the tension times cosine of 30 degrees minus F minus the force of gravity, which is the same as up here. What is the charge of each banana? For this question, we will be using the horizontal of the right one this time. We will be using sum of forces of the horizontal forces of the right banana is equal to mass times the horizontal acceleration, which would be 0, which would be the electric force minus tension times the sine of 30 degrees. We know that because this is 0, we know that electric force is going to be equal to tension times sine of 30 degrees. And now from there, we have to change the electric force into its equation, which is Coulomb's constant times the absolute value of charge 1 and charge 2 over their separation distance squared. We have this. Now we can manipulate it to then plug this into our equation, where we get K, Q, and Q. R squared is equal to T sine of 30 degrees. Well, we know that because our two bananas are equally charged, we know that charges are going to be the same, so we can instead rewrite this part as q squared. From here, we have to manipulate the equation in order to get our charge. We can get it from dividing both sides by k and multiplying both sides by r squared. So then we end up with q squared is equal to tension sine 30 degrees r squared divided by k. Since we know that sine of 30 degrees is about 1/2, we know, and since we know the force of tension is about 180, we can deduce that this here is equal to about 90 newtons. So we can change this to 90. When we square root both sides in order to get q by itself, we notice that r squared divided in the square root of that is just r. You know that distance between the two is going to be 2.0 meters as well. So that this r squared is going to become 4. And we know that Coulomb's constant is going to be 9 times 10 to the 9th. And look, we have a 9 here and a 9 here, so we're gonna source out, we get 1 and 10. We get 10 times 4, which is 40. 1 times 10 to the 9th. We do this, and we end up with 4 times 10 to the negative 8th. And we have to do the square root of that, which ends up being 2 times 10 to the negative 4th, which is equal to q. This could be rewritten instead of this as 200 microcoulombs. Thank you for watching.